All right. So hope you enjoyed the previous lecture. Here we are going to continue with the second part of our three-part lecture titled as Chapter 3 of the REMEDI module. In this lecture, we are going to delve a bit into the technical aspects of machine learning. Don't worry, it's not still that deep, and I'm not going to discuss the technical aspects in terms of mathematical equations and formulations. Still, it should be understandable, of course, by those people who have already been involved in applying machine learning in their research area, but absolutely for those who are interested and want to start this journey with us. Here we go. So if you remember in the previous lecture, we have highlighted the fact that there is a difference between traditional programming and the way that the learning algorithm in machine learning is doing its job. Let's give you an example. Assume that we are going to write a program that takes, let's say, a number and gives you that many number of the Fibonacci sequence. So what we need in order to write this program? First of all, we need that number. For example, I want the program to give me the first 100 of the Fibonacci sequence. So that's what we call it here, data. And the second and the most important part of this program should be explicitly writing, or in other terms, hard encoding, the algorithm that we expect the program to implement and compile line by line. This is what we call program. And as the result, of course, we are expecting that many numbers that we ask the program to produce for us. But in machine learning, the learning algorithm doesn't expect us to explicitly mention the relationships between the input and the output. Whereas the machine learning algorithm asks us the pairs of inputs and the outputs and can predict for us the result for the out-of-box data. So what's actually the meaning of this? It means that the network or the machine learning algorithm is trained based on the previous experiences, and in future, because it has learned the relationships between the pairs of inputs and the outputs, it can give us the prediction. So this should be a brief comparison between the traditional programming in computer science and the machine learning. Don't worry, in future slides, it should be much clearer for you. Let's start with when and where we use usually machine learning. These are a few examples that we face every day in our everyday life. For example, human expertise doesn't exist. There is a time and a place that we need extra hand. And machine learning, as we mentioned previously, can be an extra hand for us. For example, in the mission we had to explore and navigate on Mars. Another example, when and where human can't explain their expertise. Speech recognition. This is pretty clear, right? Where else machine learning can be used? Models must be customized. For example, in designing and producing personalized medicine. Models are based on huge amount of data, for example, in genomics. Human brain, of course, is very strong. Nowadays, computers, of course, are not strong enough to compete with human brain. But as we know, we cannot process huge amount of data at the same time. And this is where machine learning makes expert. However, we know that learning isn't always useful. There is no need, for example, to learn to calculate the payroll. This is what we can do, right? So this is highlighting the fact that machine learning is not a replacement for human expertise. Machine learning is only capable of giving us an extra hand. Another examples of when we use machine learning is recognizing patterns, facial identities or facial expressions, handwritten or spoken words, and also medical images. Another area is generating patterns, generating images or motion sequences, recognizing anomalies, unusual credit card transactions for the banks and the insurance companies is very important, unusual patterns of sensor readings in a nuclear power plant. Wow, pretty dangerous, right? So, of course, we need to understand the unusual patterns, where it should be, it's going to be super costly if we weren't aware of the fact of this unusual activity otherwise. And as the most classical application of the machine learning that probably 90% of the researchers are relying on that sole definition is the prediction, which in my view is pretty wrong and somehow underrating the applications of machine learning. But the prediction, future stock prices or currency exchange rates. So this is what the people actually have used and benefited from machine learning, pretty aware of, that machine learning are good in prediction. But the above examples are showing that it's quite versatile. All right, so with these images, probably it could be much clearer for you that what we mean by facial recognitions and detecting the patterns. For example, in learning of object parts, in everyday use that we are using our phone, for example, in order to unlock our phone, this technology is behind the phone. And of course, we know that machine learning is doing the job for us. In scene labeling via deep learning, autonomous cars, we know that for the cars, in order to detect between a human, road, and other objects in the street, it needs to classify the different objects in the point of view of the camera that the car has. And here is what deep learning steps in and helps the cars. In inference from deep learned models, for example, generating posterior samples from faces by filling in experiments. So as you can see in the image that we have used here, the input image on the top row, and the samples from feed-forward inference, don't worry, we don't need to discuss about the details, just our main goal here is to capture the general idea. And then at the end, in the last row, we can see somehow the effect that the middle row has on the input images, and we can see somehow the combining effect that we have on the last row of the images. This is pretty cool, right? And another example can be the impact of deep learning in speech technology. Nowadays, we have a bunch of tools, translators, our phone has, either in iPhones we have Siri, that we are asking some questions from those bots, and it gives you the answer. The technology behind is the speech technology and the speech recognition. Let's delve into a bit the technical aspects of machine learning even more. So what are the types of learning behind the machine learning? We have categorized the machine learning types, machine learning learning types, into 4 categories. Supervised learning, where we are giving the training data and also the desired outputs, and we are expecting the machine learning to learn this relationship, as we discussed in the previous slides. In the unsupervised learning, we are giving the training data, but we are not introducing the labels. So here we are only expecting the machine learning algorithm to understand the patterns and gives us some information about the data, otherwise human experts couldn't actually get any information from. In the semi-supervised learning, we have training data and a few desired outputs. So here we are combining somehow the supervised and unsupervised. And in the reinforcement learning that is behind most of the technologies like autonomous cars, speech recognition, and even in the designing the games, here we are relying on the rewards from sequence of actions. This is exactly the way that, for example, a kid learns how to walk. He stands up, he fell, and then he learns, okay, this is the balance I should, this is the amount of pressure that I need to put on my right foot or on the left foot, and slowly the kid can learn how to walk. So, and also in a lot of steps in our life, we are doing the same, right? We are learning from experiences. The experience is negative, so we are learning that not to do again the same, not to repeat the same experience. And if we gain some benefits from that experience, of course, we are going to repeat the same, right? And even more. In the supervised learning and very famous area called regression, we are receiving the pairs of numerical data instead of labels. Here, of course, we are going to have the numerical versions of the labels, which are some quantities, numerics. And this function task is actually to predict y based on the given x. And the regression is going to fit a curve to these bunch of samples and pairs of data we have. For example, here we can see the example of the September Arctic sea level extent in different years. We have sampled bunch of data, and we are expecting the machine learning model to fit a function, to fit a curve to these data. And this is where the regression or machine learning regressor is doing the task for us. Another typical application of the supervised learning is classification that we have already discussed about, images of cats and dogs, right? Remember? So here we have given the network or the model machine learning algorithm bunch of data. Here our y is actually some labels: cats, dogs, benign, malign. So, and we are expecting the machine learning algorithm to predict the labels based on the input data. Here we can see that we somehow expect, based on the tumor size, the machine learning algorithm inform us about the version of the tumor, either it's benign or malignant. All right, this is another part of the example that we can see that in a continuous axis, it can also predict for us. Another example can be the input data X can be a multidimensional domain, and each dimension corresponds to an attribute. Again, the same example that we made in the previous slide, tumor size, and we are somehow relating this attribute, this feature, to the age to see either there is any relationship between different features of the input data we have. So here, as we mentioned, X is not anymore simply the age. It is two-dimensional data, age and tumor size. And we are in a multidimensional domain. We are classifying based on these two features, the benignity and malignity of the tumors. All right, unsupervised learning. As we mentioned here, we don't have any idea about the labels or the outputs, Y's of the data we have. Here we are solely relying on the X's. And it will collapse into tasks such as recognition, pattern recognition, and clustering. So assume we have been given the left part of the data, Sorry. The data, mostly gray, we have no idea of the labels on the left part, and then we have been asked to predict different clusters of the data. And at the right, we can see that, all right, based on probably the distance, Euclidean distance, we could predict or cluster different bunches of data that are closer together and are somehow making a group that has some specific characteristics next to each other, and we are clustering them into different groups, and each of those groups have similar characteristics. All right. So, in a nutshell, designing a learning system has several steps that we need to take. But the first one is to choose the training experience. As the second step, we have to exactly know and choose what is to be learned, the target function. This is very important, right? And probably we mean somehow the supervised way, right? Because in the unsupervised way, of course, we knew the target, but mainly we are trying to understand the dynamics into the data that we were otherwise blind about, the data structure. In the third step, we need to choose how to represent the target function, mostly in mathematical form, that we usually call it cost function, and we are trying to minimize the cost, and in that sense, the machine learning algorithm is giving us better accuracy. In the next step, we are going to choose a learning algorithm that can infer the target function from the experiences. And those experiences, as you know, is the pairs of the x and y, inputs and the outputs. And when we are introducing these 4 steps and implementing it into the environment and the experience, in a nutshell, we have training data that the learner is going to receive as the input, and then is going to produce the knowledge, the dynamics, the learned algorithm based on those training data or the experiences, or even from the environment. At the end, we need to assess the performance of this learning algorithm. So what we do is actually, instead of using all the data we have in hand, we are going to split the data we have. For example, in the 80% portion and 20%, we are going to ask the machine learning algorithm to learn based on the portion, the bigger portion. And then in order to make sure that the machine learning algorithm can actually learn the dynamics over the training data set, we are going to test it. But how? Of course, on the data that we haven't introduced yet to the network. So why we are doing this? It's actually clear, because we don't want the machine learning algorithm to mimic the data structure for us, or to recall exactly, memorize the dynamics of the data. This is not like very complex task, but this is a rule of thumb, right? We don't want to put our all of our eggs into one box, right? So we are going to separate them. We are going to ask the network to learn on the first portion, and then we are going to, in order to assess the learning, we are going to take some exams from the network, right? All right. And here we have reached to the end part of the part 2 of our series of lectures on the application of machine learning in environmental sciences. And in the next part and the last part of our chapter 3 remedy module, we are going to discuss the application that I personally I'm involved with, which is exploiting machine learning in uncertainty quantification, in predictive modeling. Hope this part was useful for you.